First, the problem. I think several people have mentioned the problem is the Army and military needs to do more with less. So more intelligent force, more accuracy, keep humans out of harm's way, reduce costs, reduce costs, reduce costs, reduce costs. As I go through this presentation, you're going to notice there is a small video running in the, hopefully it's running in the lower right corner of the display. You can't see that. When we get to the end of the display, or end of this presentation, I'll tell you what's been going on. So generally, we say and look at history, solving a problem where you need to do more with less means automation. Automation means machines. Machines have been used since man has started to go beyond caveman days. They build tools, they build better tools, they build automation tools to increase speed, increase power, accuracy, keep humans out of harm's way, and be able to mass produce capabilities, thus reducing costs. And we talk about machines doing work that skilled humans have done in the past, and our focus is machines doing much of the work that skilled humans have done in the past. If you remove a lot of the humans that have high cost components, you save lots of money. So one of the approaches to do automation is to do what you've been doing for the last 100 years of automation. Hire people, build more systems, use the same techniques to manufacture hardware, build more complex systems. F-35 is an example of a probably pretty impressive machine. Costs a lot of money. Costs a lot of money to fix. Costs a lot of money to maintain. And potentially it gets so complex nobody has a clue of any one component and how it operates. So what we're focusing on is maybe there needs to be a different approach to the whole problem of automation. So first we'll ask the question of why hasn't everything been automated today? And what we're going to do is suggest that it's not the mechanical stuff, it's the cognitive processing that humans can offer that machines have not been able to offer before. So humans use human experts, whether they're an expert operator, an expert warfighter, an expert service technician. They use judgment and reasoning in solving problems because all their problems haven't been scripted. So they have to use kind of their experience to solve problems. So what we're talking about here is maybe if we offered a way for machines to do more than just if-then-else logic, which is what computerized machines have been doing, maybe that would give you a way to solve some of the problems that have been difficult or impossible to automate in the past. So the key lines in that second bullet down there is judgment and reasoning allow humans to dispense their expertise to solve problems. That isn't what machines have been doing in the past. Maybe they can do it in the future. So this has been too hard, and what we're going to suggest is until now. So maybe this is a paradigm shift in automation, which covers not just the military aspects, but almost everywhere. So hopefully this is not clinically appropriate anymore, left brain, right brain, but we're going to use that paradigm to describe the problem. And left brain computing is what computers have been doing. They process information sequentially, they process rules, if-then-else logic, is what computers do. They do that rapidly, they do a very good job of processing rules, and programmers that develop these complex systems write very complex if-then-else sets of rules to solve complex problems. But that's not judgment and reasoning. Right brain functioning is more of an image processing function. It's a value of information processing. So humans are processing weighted values of information to make judgmental decisions. And that's kind of what the right brain does. It processes information collectively. Collectively is different than parallel processing. Parallel processing's been around for a number of years. Collective processing means when you're driving your car and you're going around a corner, your car starts to slide, you're not mathematically processing if you're at this speed, if your car is sliding this much, if you're doing something else with the brakes, if you're doing this with the steering wheel, and then deciding how to correct. If you did that, you'd wreck your car. So what a human does is when they use judgment, they look at their surroundings, they make a corrective action, they observe their corrective action, they correct back until they're back on their planned path. That happens very quickly. It's analog, by the way. Somebody earlier today was talking about how the wonderful age of digital computing. We're going to suggest that, hey, the world is analog. It's not digital. You've been forcing it into a digital age because you know how computers work. What happens if you could work on problems that are analog with an analog mindset that could run on today's, digital computers? Oh, so we went through judgment and reasoning, and what we're talking about now is adding judgment and reasoning to software applications and devices. So now we're going to introduce Keel technology. Keel technology is an umbrella term that has two basic characteristics. It has a new way of processing information that operates like an analog computer, except that it runs on today's digital computers. The processing model is also completely different than today's if-then-else logic computing. It is a collective processing of information, and instead of how many lines of code would it take to solve all the problems of the world? A lot of lines of code. We say with judgment and reasoning, we can do it with about 3 pages or 7 pages of code. And we can solve all the problems. And that's because the way we solve it in these cognitive engines, our processing model, is the code for processing is always the same. This little 7-page chunk of code, 3 to 4K of memory, is always the same. The problem is defined in tables, arrays of data. No code in the processing. It just describes the problem or the processing space. Problem code is always the same. The other part of programming judgmental cognitive processing is that we're looking for a new way to capture, test, package, audit, and explain human-like reasoning. One of the aspects of human-like reasoning is you need to be able to explain. You ask the pilot, which you can't do anymore, the pilot of the German Wings aircraft, why did he crash his plane? Even if he was alive to crash, he probably could not explain exactly why he decided to do that. He couldn't explain with mathematical precision why he did what he did. He might have some reason, he might be able to explain something, but not to the level of a machine. So what we're offering is a new way to capture, test, package, audit, and explain complex information sets, complex being dynamic, nonlinear, interrelated, multidimensional information sets. And we're going to do that in a language that can be learned in a couple of weeks and can be done with domain experts, not mathematicians or software engineers. Easy, in other words. So the other half, this is the second half now, how do we do this, capture this complex problem-solving skill set? We have the Keel dynamic graphical language. And there are other graphical languages that have been out there before, but most of them are graphics where you have little boxes, you have arrows between boxes that define information flow. That's not how Keel works. We'll try to get a chance to show you that in a few minutes. We allow this development of the cognitive models to be done by the domain experts without mathematicians or software engineers because the designer, even when we find an expert, that expert is probably not familiar with how to describe how he or she thinks that can be put in a machine. So that expert actually has a dialogue with the language and observes how the language performs while you're defining the solution. You actually see the system think. And here's the cognitive engine. So while you're doing your development, the cognitive engine is being created behind the scenes. So you're developing it with this dynamic language. Behind the scene, the Keel cognitive engine is being developed and the data tables that define the problem set. And we're providing this almost like it's running in an analog computer. You actually can see system balance information, balance alternatives, see a value system, which is what you have to have in a system that it thinks in judgment and reasoning. And it packages it, essentially operates as a packaged human expert's capability inside of a device. That device could be one human expert inside of a vehicle, or as we talk to the automotives, there might be 50 Keel engines inside of an automobile making judgmental decisions to control functionality of the system. So you end up with adaptive machines. Humans with a value system. We now have machines with a value system that make judgmental decisions according to the policies rather than rules. We're talking about behavior of machines, not programs performing functionality. Allows the human policymakers to maintain control. So there is concern about turning cognitive systems over to a machine. In this case, the human still maintains control of the policies operating in the system. Auditability is easy to see. Now, I'm going to open it up for questions, but I'll also show you that in the bottom right corner of the machine, where we had this video running, what's been happening is from concept through 2 periods of iterations, we've developed an engagement policy for an autonomous weapon system. That's 12 minutes and 24 seconds from concept development, entering what influences the design to get solutions out that have gone through certified code review and put inside or available to give to a software engineer to put in your weapon system. We have, depending on time and questions, we have videos we can run, or I'll answer any questions. So first, are there any questions? No questions? You want a video for a minute? Okay. Can you run the first green one? Okay, just quickly. We have 2 UAVs shown up here. Each UAV has a Keel cognitive engine. Keel cognitive engine is providing several functions. It's searching for that large red dot. That's the target. The red dots, it doesn't see them. Those are defensive targets. They can shoot at the airplanes. The airplanes are also doing dynamic collision avoidance. They are, here we have an example of collision avoidance. Depending on how fast this video runs, what happens is the UAV, once it finds the target, it will try to attack the target if it can be done safely. It's evaluating its risk and reward. So this UAV is going to come up there. I don't know whether it'll attack or not. It's based on its target value, target risk. It's trying to find a safe way to attack. Those defensive targets are telling it that's not safe. It's finally coming around and saying, I give up. I've damaged so much. My policy says I should go home. We also have mission control. So instead of remote control, we're suggesting that you can use a mission control to change how the UAV thinks. So we're not taking remote control of the UAV. We're changing how it interprets the situation. One of the ways we can do that is tell the UAV that we think the target is more important than you thought it was, and we want you to be more risk tolerant. In this case, this UAV is going to try and go around. He's going to get frustrated, and he's going to go home. Right now, we're going to say, okay, what I'm going to have you do is cancel this, and we're going to quickly go to the next demo. That's the one in the middle. Back up. You just need to arrow click on that. Okay. This is the Keel dynamic graphical language. So if you're familiar with source code, if then else stuff, this isn't it. This is a dynamic graphical language. The bars at the top are indications of importance of information. Those can either be outputs or information fusion points. The height of those outputs is an indication of importance of information. Information can change in importance based on time, based on your situation, based on stress. We show this as a dynamic language. By the way, the bars on the bottom with the green arrows pointing up, those are reasons to do something or supporting arguments. Red ones pointing down, reasons not to do something or rejecting arguments. As we move the information around here, you'll see the entire system balance alternatives to make decisions. It is an analog system, balancing. We click on those wires. Wires define functional relationships between information items. Isaac Newton invented calculus. All he had was a pencil and paper, define all these complex little relationships. That's the definition of calculus. We have a graphical display. We define complex functional relationships easily. So one of our next speakers is going to talk about how easy this can be done and embedded. You can trace wires to define why things happen. So when you're auditing the behavior of an autonomous system, decide why it did what it did. So assuming you have a pilotless aircraft in the future and it does something bad, either because of bad sensor data, bad information, you can trace back easily and see why. I think I'm being flagged and it says time's up.